Hello, this is Professor Salil. Welcome back to our discussion on convection. In the first part of this lecture, we had looked at the basic concepts of convection and also introduced the concept of the velocity and thermal boundary layers. In today's session, we are going to look at the fundamental governing equations which are of interest in solving convection problems, and we will also get introduced to the concept of turbulence in fluid flow. So there are basically three important governing equations which are used in convection problems. The first one is related to the conservation of mass, and it is called as a continuity equation. The second is related to the conservation of momentum, which is described by the Newton's second law of motion, and this, in the case of fluid mechanics systems, we call the equation as Navier-Stokes equation. The third one is the energy conservation, which is described by the first law of thermodynamics. We call it as the energy equation. There is no specific name as far as I am aware. So we will start with the first governing equation, that is the conservation of mass, also called as the continuity equation. In this lecture, we are not really going to look at the complete derivation, but I will just give you the basic framework of how these equations are developed. We will look at the basic building blocks without going into detail about the mathematical derivation involved. So we will look at one small element of fluid inside the domain of fluid flow. As we said, we are making some simplifying assumptions here. For example, we are only going to look at two-dimensional flows. The dimensions of interest are the direction of flow, which we denote as x, and the direction normal to the wall, which we call as the direction y. The third direction, which is normal to the screen, that is the z direction, is not of importance. So we will only consider the x and y directions. So it is a two-dimensional fluid flow case. We are also neglecting variations with time, so that we will make use of the steady state assumption. The third assumption that we are using is that of an incompressible fluid. Essentially, it means the density remaining constant. This is true for most of the liquids. Also, in the case of gases which have got a very low velocity, typically with Mach number below 0.3, those gases can also be assumed to be incompressible nature because their density variations are almost negligible. So if we look at this fluid element, which has got a dimension of dx in the x direction and dy in the y direction, the inflow and outflow are indicated by the velocity components. U is the incoming flow in the x direction, and u plus dou u by dou x dx is the outgoing velocity in the x direction, as given by the Taylor series expansion. Likewise, we have got velocity components in the y direction. So for mass conservation, the statement that we are going to use is that the rate of mass inflow equals the rate of mass outflow. So if you look at this carefully, we can see that the net flow in the x direction will be the difference between the incoming and the outgoing flow. So that will be given by dou u by dou x dx into dy, because dy represents the area. So there is a corresponding component in the y direction also. So if we add up these two components, the net inflow becomes 0, and the equation simplifies to dou u by dou x plus dou v by dou y equal to 0, which can be also expressed using the del operator as del dot of the velocity vector is equal to 0. So this is the simplest form of the continuity equation, subject to the assumptions that we have mentioned just now. As we have seen in the first slide, we are going to describe the momentum conservation equation based on Newton's second law of motion, and here again we are going to make the assumption of a 2D steady and incompressible flow of a Newtonian fluid. Now, since we have two directions to consider, that is x and y, we need to have a different equation in each of these directions, so that we have an x momentum conservation and a y momentum conservation. So the statement of the momentum conservation reads like this: the net outflow rate of momentum, which commonly be expressed as the product of the mass and the acceleration of the fluid, equals the net force acting on the element in that particular direction. For example, if you are looking at the x direction, the net outflow rate of momentum in the x direction equals the net force in the x direction acting on the element. When we are discussing forces, there are two types of forces that we should consider here. One is the body force, which acts throughout the control volume, some examples being gravity, electric forces, etc. So these forces are proportional to the volume or to the mass of the body, of the fluid element. The other type of forces are called as surface forces, which act on surfaces, examples being pressure and viscous drag. So these forces, the surface forces, are proportional to the surface area. If we are considering the forces per unit volume of a fluid element, we can write the x and y momentum equations as given here based on the above statement. The left hand side represents the product of the mass per unit volume and the acceleration in the x direction. The first equation here is the x momentum equation. Second equation is the y momentum equation. So we will have a look at the x momentum equation first. So the mass per unit volume is the density, and the acceleration in the x direction is given by the term here in the square brackets. On the right hand side, we have got the forces acting in the x direction. Bx is the total body force acting in the x direction per unit volume, whereas dou p by dou x is the pressure force, which is a surface force acting in the x direction. Further, we also have the stresses induced by viscosity. Sigma xx is the normal stress in the x direction, and dou yx is the shear stress acting in the x direction. Thus, the right hand side is the net effect of all the forces in the x direction. Further, these terms like the viscous stress terms can be expressed in terms of the corresponding velocity gradients, in which case we get the final term involving the viscosity and the second derivative of velocity. So this form is what we call as the Navier-Stokes equations. So this is the equation for the x momentum. There is a corresponding equation for the y momentum. You can see that the x momentum involves derivatives of the x component of velocity, that is u, and the y momentum equation involves the y component of the velocity, that is small v. We can also express the total momentum conservation in a vectorial form using the del operator as given in the final expression here. The third governing equation that we are interested in is the energy conservation equation, which is based on the first law of thermodynamics. Subject to the assumptions that we have listed earlier, and considering a small fluid element of dimensions dx, dy and unit thickness in the z direction, we can write the energy conservation statement as follows: the rate of net heat input into the element plus net work input to the element plus the net energy inflow by mass into the element is 0. If we neglect radiation, the net heat input into the element is by conduction, and that is given by the formula given here: k dou square t by dou x square plus dou square t by dou y square times dx dy. Similarly, the net work done by the body forces is expressed in terms of those body forces and the corresponding velocity components. Again, the net work done by the viscous forces are also expressed in terms of the corresponding stress components and the velocities. The last term here is the net rate of energy inflow into the element. So there are two directions to be considered. So this is the net inflow in the x direction, and this is a net inflow in the y direction. And for the energy, we are considering the enthalpy component and the kinetic energy component. Thus, the statement of energy conservation can be written as follows, including all the components that we have discussed above. If we take the derivative of all the components on the left hand side, the equation simplifies to this form, and we are also making use of the continuity equation to cancel out some of the components. For example, we will be getting terms like dou u by dou x plus dou v by dou y, which will be 0 based on the continuity equation. So we can simplify the left hand side to this form, and in order to simplify the right hand side, we will manipulate the momentum equations a little bit. We need to multiply the x momentum equation with u and the y momentum equation with v, and if we add them, the right hand side can be expressed in a form like this. If we examine this equation closely, we can see that the terms here on the left hand side occur here as well in the original energy equation that we have seen just now. Similarly, some of the terms on the right hand side are also common to the energy equation that we had seen initially. So if we compare the terms, we can simplify our original energy equation to a form like this. The benefit of doing this is that we are eliminating a lot of terms and we are retaining the terms which involve enthalpy, which is the actual component of energy. So the energy equation takes a form like this, which can be further modified based on the relationship between enthalpy and internal energy, and also by using the definition of the viscous stresses. The equation for the normal and the shear stresses are given here in terms of the corresponding velocity gradients. So if we substitute all of these expressions into the energy equation, the final form, which is much more compact, becomes like this. So this involves the enthalpy, temperature and the pressure terms, and one final term which is the effect of the viscous stresses. So this term phi here is called as the viscous dissipation function, which involves the velocity gradients. That actually represents the work done by the viscous forces, or rather the energy dissipated by the viscous effect. So we can have the energy equation in terms of enthalpy or in terms of the internal energy. And in the case of an incompressible fluid, recognizing that the specific heat Cv and Cp are equal, and we can write the internal energy in terms of temperature, the final form of the energy equation can be in terms of temperature as follows. This completes our discussion on the governing equations of fluid flow. Next, we will have a look at the effect of turbulence in fluid flow. In our previous discussion on the growth of the velocity bound layer over a flat plate, we had described that initially the velocity bound layer is going to be laminar in nature, because the flow is going to be orderly and streamlined in the initial stages. Whereas after a certain distance, we have seen that there is a transition to turbulence. This is characterized by a highly random, fluctuating and disorderly flow. And we have also seen that the transition is not instantaneous, but it occurs over a distance. Initially, there will be some small disturbances in the flow which can die out for a certain period, so that the flow keeps fluctuating between laminar and turbulent, and after a certain distance it consistently becomes turbulent. So that is the transition to turbulent flow. One of the earliest experiments to visualize the transition to turbulence was given by Reynolds, who used a dye injected into water flowing in a glass tube to look at the effect of turbulence on the flow. He also looked at the transition of the flow from laminar to turbulent. So what he observed was that if we are injecting the dye into a laminar flow, the streak of the dye stays unmixed. It flows parallel to the flow for a very long time before it mixes. But when he increased the flow rate, he found that the mixing is much more rapid, because at some stage with increased flow rate, the flow becomes turbulent, and there is a very rapid mixing which occurs as shown in this diagram, so that the dye does not remain in its original path but gets immediately dispersed within the fluid. So the important question is, what actually causes turbulence? Typically, the viscosity induced shear in fluids result in the formation of some unsteady flow structures, which we normally refer to as vortices. These vortices can grow and get amplified over a period of time, and they can cause turbulence. Other causes of turbulence are disturbances in the flow. For example, if the flow varies from time to time, it can cause disturbances in the flow, which can again lead to turbulence. Also, the surface roughness of the plate or the pipe, etc., can lead to turbulence generation. Similarly, vibrations of the surface or the pipe can also result in turbulence. We can determine whether a flow is laminar or turbulent based on the value of the Reynolds number. Normally, if the Reynolds number exceeds a critical value, we say the flow is turbulent, and below the critical value, we consider the flow to be laminar. In the case of a flat plate, the critical value of Reynolds number is about 5 into 10 power 5. Reynolds number is described as the ratio of the inertial force to the viscous force, and has an expression like this in terms of the velocity, the distance or a dimension, and the viscosity. We can derive this expression of Reynolds number as given here. It is the ratio of the inertial force to the viscous force. The inertial force is expressed as a product of mass and acceleration, whereas viscous force we can describe as a product of viscosity, velocity gradient, and area. Using the symbol L to represent all the length dimensions, we can describe the mass as a product of density and volume, so that becomes rho into L cube. Acceleration is velocity divided by time, so velocity divided by L by V. L by V is indicating time. Similarly, in the denominator we have got mu. The velocity gradient is denoted as V by L, and the area as L square. So if we simplify this expression, we get rho L square V square by mu VL, which further simplifies to rho VL by mu, which is the expression for Reynolds number. The L here is any characteristic length dimension. In the case of a flat plate, this is the distance from the leading edge. If you are looking at flow in a pipe or inside a channel, we will use what is called as the hydraulic diameter for the characteristic dimension. Next, we will look at the mechanism of turbulence and also some characterizing features. As we said, at low Reynolds number, the flow remains laminar. This is because at these low Reynolds numbers, the viscous forces exceed the inertial forces as indicated by the expression of Reynolds number, so that the viscosity will tend to dampen out the fluctuations in the fluid. They will die out and we don't have turbulence. But as inertial forces dominate, the fluctuations will increase and the viscosity cannot keep the fluctuations down. So the increasing fluctuations are manifested as turbulence at high Reynolds number. In turbulent flow, all the parameters such as velocity, temperature, pressure, etc. show random fluctuation, so that these parameters are commonly expressed as a sum of a mean and a fluctuating component. As shown here, the quantities with an overbar are the mean quantities, and the quantities with the dash or the prime are the fluctuating parameter. As we know, in laminar flow, the flow is characterized by very orderly flow which occurs in layers or in stream tubes, etc. So there is no mixing between these layers. There is no flow across streamlines, and the mixing occurs only because of the molecular effect. That is what we call as diffusion. In turbulent flow, we find swirling structures which we call as eddies or vortices. These transfer large quantities of mass normal to the surface. So if we are looking at a flat plate with a one-dimensional flow, that means we only have the u velocity. Even in that case, we still have the v prime component because of turbulence. So that means there is a flow normal to the plate or normal to the surface caused by the turbulence. So this will rapidly enhance the mixing process. This is something which was not present in the laminar flow because all the fluid was flowing in layers without undergoing any cross flow. And turbulence, on the other hand, is characterized by the cross velocity components, which enhances the mixing. This results in a very rapid exchange of momentum and heat in the turbulent flow. So in turbulent flow, we encounter very large gradients of velocity and temperature at the wall. So correspondingly, there will be greater wall shear stresses and heat transfer rates compared to the laminar flow. The thickness of the boundary layers are also greater in the case of the turbulent flow. Now we will have a closer look at the turbulent boundary layer. As we have seen earlier, after the transition region, the flow becomes entirely turbulent, which is characterized by fluctuating components in the flow as shown by these arrows here. These are the eddies that we have discussed in the previous slide. The turbulent boundary layer is made of three distinct zones. Very close to the surface, we have what is called as a laminar sublayer. This means that even if the flow in the boundary layer is turbulent, very close to the surface, for a very small distance, we have a laminar flow. That is because near the surface, the viscous forces are dominant, and that prevents the fluctuations and maintains the flow as laminar. So here in the laminar sublayer, the mixing is only because of the molecular diffusion. Far from the wall, we have a fully turbulent zone, which is shown here, and here the eddies are predominant, and the turbulent mixing happens with a large amount of momentum and heat exchange caused by the eddies. In between the laminar and the turbulent layers, there is a buffer layer where the mixing by turbulence and diffusion are comparable. In other words, the inertial and viscous forces are of comparable magnitude in the buffer layer. The viscous forces dominate in the laminar sublayer and inertial forces dominate in the turbulent layer. Because of the mixing happening in the turbulent and buffer layers, we have almost uniform velocity in these two layers. So there is hardly any velocity variation occurring in the buffer and turbulent layers. So we can find almost a very flat velocity profile in these two layers. And that also means that the bulk of the velocity rise occurs in the laminar sublayer. Recall that the velocity has to increase from 0 at the wall to 99% of the free stream velocity in the boundary layer. So since there is not much change occurring in the later two zones, almost the entire velocity increase happens within the laminar sublayer, which is a very thin layer. This results in a very high velocity gradient in the laminar sublayer, resulting in high wall shear stresses. So here we are comparing the laminar velocity profile and the turbulent velocity profile. As we can see, the turbulent velocity profile is much more steeper than the laminar one, with a very high velocity gradient at the surface. So here we have a question. This is related to the thermal boundary layer. So in which boundary layer we will have a higher value of the convective heat transfer coefficient, laminar or turbulent? The answer lies in the fact that the heat transfer coefficient is proportional to the temperature gradient, as we have seen in the first part of the lecture. And by the same argument that we have used here, the temperature gradient is also going to be greater in the turbulent boundary layer compared to the laminar boundary layer, and hence the heat transfer coefficient is also going to be greater in the turbulent boundary layer. When we are solving the governing equations in the boundary layer, we can make some simplifying assumptions. For example, if we are looking at the laminar boundary layer, the velocities normal to the wall, that is in the y direction, these are denoted by the symbol v, are negligible compared to the velocity along the wall, that is u. So v being very small compared to u, we can neglect the derivatives of v as well as the terms involving v in the governing equations. So we have dou v by dou x and dou v by dou y approximately equal to 0. Another interesting fact in the boundary layer is that the gradients along the flow direction are negligible compared to the derivatives in the normal direction. That is, terms like dou by dou x are negligible compared to the dou by dou y terms. This is because velocity and temperature and other parameters undergo very rapid change in the y direction because of the boundary layer effect. So the gradients are also more dominant in the normal direction compared to the flow direction. That means that dou u by dou x is much smaller than dou u by dou y. Similarly, dou t by dou x is much smaller than dou t by dou y, and so on. Based on these assumptions, and also if we neglect the body forces, we can simplify our y momentum equation considerably, because y momentum equation predominantly contains terms which involve the v component of velocity. So the y momentum equation now reduces to dou p by dou y equal to 0. That means the pressure does not vary normal to the wall. Pressure varies only in the flow direction, and it does not vary normal to the flow direction. In other words, the pressure within the boundary layer will be equal to the pressure in the free stream above if we go normal to the wall. This is significant because if you want to measure the pressure close to the wall, that becomes very difficult, because putting a probe close to the wall will disturb the flow, will disturb the boundary layer, and the measurement becomes inaccurate. On the other hand, it is much more easier to take the reading far away from the wall. So in effect, we can take the pressure reading in the free stream, and that will be equal to the pressure within the boundary layer. For the special case of a flat plate with constant free stream velocity, that is u infinity as a constant, if we apply the x momentum equation to the free stream, because of the constant velocity, we have all the gradients of the u component also becoming 0. So dou u by dou x, dou u by dou y are also 0. In addition, the terms involving v are also 0, as we have seen earlier. So this gives us dou p by dou x equal to 0. That means the pressure remains uniform everywhere for a laminar incompressible flow without body forces over a flat plate, subject to the condition that the free stream velocity is constant. Next, we will look at the concept of the similarity and non-dimensionalization of governing equations. If we neglect the viscous dissipation terms, the governing equations for a 2D steady laminar flow of an incompressible fluid without body forces and constant properties can be non-dimensionalized to give them a form which is of a normalized nature. So we can non-dimensionalize the x and y dimensions using a characteristic dimension L. So x by L, we will denote it as a non-dimensional number x star. Similarly, y star is y by L. The velocity components can be non-dimensionalized using a velocity v as shown here. Similarly, we will also non-dimensionalize the pressure and the temperature. Once we do that, the continuity, momentum and energy equations will take a form involving only the non-dimensional parameters like u star, x star, etc. Also, notice that we no longer have the properties like k or mu occurring in these equations. Instead, we have the non-dimensional numbers like Reynolds number and Prandtl number. Also, by non-dimensionalization, we can transform all the boundary conditions to values like 0 and 1. We no longer have velocity or temperature values for the boundary conditions, but only constant values like 0 or 1. These two boundary conditions here represent the condition at the leading edge, because here the x star value is 0. In other words, x is 0, so we are looking at the leading edge in these two cases. So at the leading edge, the velocity is same as the free stream velocity, so that the u star value becomes 1. Similarly, the temperature is also the free stream value, so the T star value also becomes 1 according to the definition given above. The second set of these values are for y star equal to 0. In other words, y equal to 0 representing the wall. So at the wall, the velocity is 0, so u star also becomes 0. The temperature at the wall is Ts, So the T star value at the wall becomes 0. The third set is for the free stream for y star tending to infinity. That implies y becoming infinity or the free stream condition. At the free stream, the velocity is a free stream velocity. So u star becomes 1 and T star becomes 1 because T becomes T infinity, and according to this definition, T star becomes 1 in the free stream. The last one is again for the wall. The value of v star, the v velocity component at the wall, will be 0 because of the no slip condition. So why do we do the non-dimensionalization? This brings the equations to a consistent form and also make the boundary conditions to be equal for all the geometries of a given type for all the flow conditions. That is very important because now the equations and the boundary conditions no longer have specific values like the velocity components or the temperatures, but they are the same for all the flat plates, for example, and for all flow conditions, whether we are looking at velocities of 5 meter per second, 10 meter per second. In every case, the set of boundary conditions will be the same and the set of governing equations will also be the same. In other words, solution becomes independent of parameters like the length dimension, the velocities, temperatures, and even the flow properties. Since we are dealing with non-dimensional numbers like Reynolds number and Prandtl number, we no longer have the fluid properties coming into the equation. So the solution now becomes identical for flows with the same Reynolds and Prandtl number. That is another advantage of using the non-dimensional form of the governing equations. So these numbers are called as the similarity parameters. So even if the geometric and flow parameters are different, and even for different fluids, even if we are, let's say, considering water and air, so long as the Reynolds number is the same, we can use the same momentum equation for the two different fluids. This slide briefly explains the derivation of the non-dimensionalized governing equations. The continuity equation for a two-dimensional steady incompressible fluid was specified as dou u by dou x plus dou v by dou y equal to 0, as we had seen earlier. If we multiply this equation with L by V, that means we are dividing the numerator with V and we are dividing the denominator with L. We get this form of the equation: dou of u by V by dou x by L plus dou small v by capital V by dou y by L equal to 0. So u by V is nothing but non-dimensional velocity u star, and x by L is x star. Similarly, v by capital V is v star and y by L is y star. So the final form of the governing equation in the non-dimensional form becomes dou u star by dou x star plus dou v star by dou y star equal to 0. This is for the continuity equation. The x momentum equation for a two-dimensional flow with a body force Bx is shown here for an incompressible fluid. This is a Navier-Stokes equation for the x momentum. Also, the assumption that we have discussed earlier was that the body force is 0, and as we seen earlier, the gradients in the x direction can be neglected. So dou square u by dou x square becomes 0. See that we are not neglecting this component because it gets multiplied by u, so that it becomes an appreciable number. Likewise, even though we are having v here, we are not neglecting this term because we have dou u by dou y. So it's a product of a large term and a small term. Similarly, here also it's a product of a large term and a small term. So we cannot neglect anything on the left hand side. On the right hand side, we are neglecting the body force and the second derivative of the x component of velocity. Also notice that we are using the derivative dp by dx rather than the partial derivative dou p by dou x. This is because we have seen that the pressure varies only in the flow direction and does not vary in the y direction. So p becomes a function only of x. So we can use the complete derivative dp by dx here. Now this equation needs to be multiplied by L by V square. Like what we did for the continuity, we are multiplying the x momentum equation with L by V square. In other words, we are dividing the numerator with V square and we are dividing the denominator with L. So our equation becomes like this: U by V replaces U and x by L replaces x, and so on the left hand side. On the right hand side we have got mu coming here, and I am dividing this U term with V. I still have one more V left that I am using on the denominator. Similarly, I need to divide the denominator with L as we have seen here, but since I have x square here, I should divide it with one more L. So I am using L square. So correspondingly I am using an L here. I am multiplying with L and dividing by L in the denominator. Same thing goes for the second term within the brackets. For the pressure derivative, I am bringing the density term into the derivative. So I have P by rho, and again I am dividing the numerator with V square and the denominator with L. So now if you see this one, this is U by V is U star. Similarly, x by L is x star, and see, we have mu by rho VL. Remember that rho VL by mu is Reynolds number, so this term here becomes 1 by Reynolds. So here again we have dou square U star by dou x square, dou square U star by dou y square, and so on. This becomes dP star by dx star. So that gives us our final form of the non-dimensionalized x momentum equation as shown here. We need not write the y momentum equation because, as discussed before, the y momentum equation boils down to simply dp by dy equal to 0. I will leave the derivation of the non-dimensionalized energy equation as an exercise for you, so you can check if you are getting the equation as we have displayed here in this previous slide. So the energy equation upon non-dimensionalizing should take this form. We will get the Prandtl number in the energy equation. Next we will look at the procedure for determination of the friction factor Cf and the heat transfer coefficient H. We will look at the functional dependence of these two important parameters. If you look at the non-dimensionalized x momentum equation here, we see that u velocity becomes a function of x, y, Reynolds. So u star is a function of x star, y star, and Reynolds number. Even though we have got a pressure term coming here, I didn't put pressure as one of the independent variables here. So that is the question I have put here. So why I am not including P star? The answer is that P star is a function of only x star, as we have seen before. So we need not put P star because already we have got x star as an independent parameter. So it's not really required to put P star, which is again another function of x star. Likewise, if you look at the energy equation, we will find that T star will also be a function of x star, y star, Reynolds number, and Prandtl number. Recall that the wall shear stress tau is given by mu into the derivative of u velocity at the wall. So this we can non-dimensionalize and write in the form mu v by L into dou u star by dou y star at the wall. And also the friction factor Cf can be written in terms of the shear stress. Remember that tau was half Cf into rho v square. So by rearranging the terms, we get an expression for Cf as shown here. Now substitute the value of tau from the above equation here, and it will simplify to 2 by Reynolds dou u star by dou y star at the wall. In other words, the friction factor depends on the Reynolds number and on the velocity gradient at the wall. So it is a function of x star and Reynolds. Y star does not come here because we are looking at the derivative at y equal to 0. So at a fixed location in the normal direction. So it is not a function of y star, but depends only on the direction along the flow. It depends only on the x coordinate and the Reynolds number. Similarly, the definition of the convective heat transfer coefficient H was like this, which we have discussed in the previous lecture. So this also we can non-dimensionalize. Recall that T star was T minus Ts by T infinity minus Ts. So we can make use of that to write the expression of heat transfer coefficient in a non-dimensionalized manner like this. If we rearrange these terms, we can write that HL by K is dou T star by dou Y star at the wall, and HL by K is our Nusselt number. So Nusselt number becomes the non-dimensionalized temperature gradient at the wall. This is again one of the definitions that is used for Nusselt number, that it represents the non-dimensional temperature gradient at the wall. So since our T star is a function of x star, y star, Reynolds and Prandtl, the non-dimensional gradient of temperature at the wall becomes a function of x star, Reynolds and Prandtl. So we can summarize that the value of the friction factor is a function of the x coordinate and the Reynolds number, and the Nusselt number is a function of the x coordinate, Reynolds and Prandtl number. But these two values are the local values dependent on the x coordinate at a particular point. We can also find the Cf and H for the complete geometry. That is, if you are looking at a flat plate, we can determine the average value of Cf and H by integrating over the complete distance. So since x star varies from 0 to 1, we can find the average values integrating over the surface from x star varying from 0 to 1, so that we can remove the dependence on x star. So therefore, the average value of the friction factor now becomes only a function of the Reynolds number, since we have removed the dependence on x star by averaging it. Likewise, the average Nusselt number becomes a function only of Reynolds and Prandtl number, as we have removed the dependence on x star by integration. Typically, the Nusselt number is expressed in terms of the Reynolds and Prandtl using a power formula like this: a constant into Reynolds raised to some exponent and Prandtl to some other exponent. So as we have seen, the friction factor Cf is a function of Reynolds, and Nusselt is a function of Reynolds and Prandtl number. In some cases, it is possible to express Nusselt number in terms of the friction factor, which is easier to determine. That is what we can obtain by making use of an analogy between the momentum and heat transfer. For fluids which have got Prandtl number of the order of magnitude of 1, as in the case of most of the gases, and if we have got the pressure gradient vanishing in the x direction, remember that that is the case for a flow over a flat plate with a constant free stream velocity. So the non-dimensionalized momentum and energy governing equations become identical. See that the pressure gradient term has vanished here, as we have seen, and also in the energy equation the Prandtl number has also been removed because it is of the order of magnitude of 1. So therefore these two equations, the x momentum and the energy equations, become identical. We can also see that the boundary conditions of the variables u star here and t star here, they also become identical. As we had seen previously, this is for the leading edge, this set is for the wall, and this set is for the free stream. So the boundary conditions and the governing equations become identical. This means that upon solution, we will find that both u star and t star will have similar variations. So we can write that at the wall, if we take the gradients, dou u star by dou y star will be equal to the gradient dou t star by dou y star. But dou u star by dou y star is Cf into Reynolds by 2 according to this expression, and dou t star by dou y star is the Nusselt number. Making use of that, we can state that subject to these assumptions, Cf into Reynolds by 2 is equal to the Nusselt number. This is what we call as the Reynolds analogy, which is a means of expressing the Nusselt number in terms of the friction factor and the Reynolds number. An alternative form of this equation is Cf by 2 equals the Stanton number, which is denoted by St. Stanton number is a modified form of the Nusselt number. It is Nusselt by Reynolds into Prandtl, otherwise denoted as H by rho v Cp. So Cf by 2 equals the Stanton number, and this holds good for Prandtl numbers approximately equal to 1, as we have stated in the initial assumption. A modified form of this analogy is called as the modified Reynolds analogy or as a Chilton-Colburn analogy. This is valid even for higher values of Prandtl number. So that is stated as Cf into Reynolds by 2 equals Nusselt into Prandtl to the power minus 1/3, or in other words Cf by 2 is Stanton Prandtl to the power 2/3. So this can be used to determine the Nusselt number for fluids which have got Prandtl number different from 1. Finally, we will look at some non-dimensional numbers which are important for our study of heat transfer. Some of them we have already discussed in relation to conduction, and the last set of numbers are more relevant to convection. As we have seen in the discussion on lumped capacitance systems, the Biot number Bi is a ratio of the internal, that is the conduction resistance of a body, to the external, that is the convection resistance. So for example, if we are immersing a body in a liquid, internal to the body we have a conduction resistance, and outside the body we have got a convective resistance. A comparison of these two gives us the Biot number, and the value of the Biot number is used to assess whether a system is lumped or not. If the Biot number is very small, typically below 0.1, we can say that the internal resistance is negligible compared to the external resistance. That also means that the temperature distribution within the body will be uniform. There won't be any spatial variation of temperature. That is the characteristic of a lumped capacitance system. So the Biot number is expressed as the product of heat transfer coefficient and a characteristic dimension divided by the conductivity of the solid. The coefficient of friction, also called as the Fanning's friction factor or simply friction factor, is expressed as we have seen previously, and it represents a non-dimensional wall shear stress. With regard to the lumped capacitance system, we had seen another non-dimensional number, which is a Fourier number. This is denoted as alpha T by L square. Alpha is the thermal diffusivity, small t is the time, and L is a characteristic dimension similar to that of the Biot number. So this represents non-dimensional time, as we can see from this expression. It is a way of non-dimensionalizing the time. Another definition is that it is a ratio of the heat conduction to thermal energy storage within the body. The Grashof number Gr is a ratio of buoyant forces to viscous forces. It is expressed in terms of the acceleration due to gravity, the volumetric thermal expansion coefficient beta, the difference in temperature of the surface and the free stream, the characteristic dimension L, and the kinematic viscosity nu. This is typically used in free convection, that is natural convection problems, to evaluate which force dominates, the buoyant force or the viscous force is dominating. This is also related to assessing whether the flow is laminar or turbulent in the case of natural convection. The Nusselt number we have seen earlier, it is defined as HL by K of the fluid. It's the ratio of the convection heat flux to the conduction heat flux. It is also denoted as a non-dimensional temperature gradient, as we have seen just now. Another definition is that it's a non-dimensional heat transfer coefficient. We have discussed earlier that the expressions of Nusselt number and Biot number are comparable. The only difference is that in the case of Nusselt number we are using the conductivity of the fluid, whereas in Biot number we are looking at the conductivity of the solid. So the Biot number is more related to the solid, and the Nusselt number refers to the fluid. The Peclet number is a ratio of advection to diffusion. Recall that convection, it is a combination of advection and conduction. So a comparison of these two phenomena is given by the Peclet number. So it is expressed in terms of two other non-dimensional numbers, the Reynolds and Prandtl number. So the product of Reynolds and Prandtl is called as a Peclet. The Prandtl number is the ratio of the momentum and thermal diffusivities. In other words, it's the ratio of the kinematic viscosity and the thermal diffusivity, and we have seen that this is related to the relative thickness of the velocity and thermal boundary layers in laminar flow. Reynolds number is the ratio of inertial force to viscous force, as we have seen earlier in this lecture, and it is used to assess whether a flow is laminar or turbulent. It is also used to calculate the friction factor and the Nusselt number. Finally, the Stanton number is a modified Nusselt number, as we have seen in the previous slide. So these are a few non-dimensional numbers which will be useful for our study of convection.